This is limits with trig functions. So we want to look at our two functions. We have our sine and our inverse. If we're plugging into sine, these are your possible x values here, right? And if we're plugging into our inverse, this is what we would get. So if we keep this as 1 to 1, this is our inverse here. So when we look at these, we want to focus on what's going on here. So if x approaches 0.5, well, 0.5 is right here on our function. So we're going to approach from the left and the right. It's continuous, it's defined. So you can just plug that in to a half and then use your unit circle. So for the inverse sine of a half, we would get pi over 6 or 30 degrees. And you can check that in your calculator. I've already got it set for degrees. So there it is, 30 degrees. It works perfectly. So pi over 6 or 30 degrees. Now, over here we are using pot radians, so we should probably keep it at radians, just so that we have it consistent. All right, what about -1? Well, with -1, we have this point here. So you're not going to be approaching from the left, only from the right. So that's what we have here. So as we approach from the right, you can see that we are approaching -pi over 2. And so you can use the unit circle, the same basic idea. You already know that we would be approaching -1, it would be pi over 2. They work either way. You can think about this being the y value for the sine or the x value for the inverse, as long as it stays 1 to 1. All right, tangent. Tangent is very similar, but remember we don't have defined values, no brackets. So the limit as x approaches infinity for the inverse tangent of x, that's this guy. You can see all I've done is basically just converted it into an inverse. I switched all the x's and the y's. So instead of having vertical asymptotes, we have horizontal asymptotes at pi over 2. And from the positive, we approach infinity, and from the negative, we approach negative. Just like here, we approach negative infinity on the negative, infinity on the positive. So as x approaches negative infinity, we're approaching -pi over 2. The asymptotes become the limits. So as x approaches infinity of the inverse tangent, so this way, it approaches pi over 2. So negative infinity, we get -pi over 2. Positive infinity, we get pi over 2. It approaches the asymptotes. Okay, so what if you have this? So obviously if we just have this situation, we're good, it's pi over 2. But if you throw something else in there, a different function, then we have to do is do what we did before, and we want to look at this as the limit as t approaches 0 plus tangent negative infinity to t. And it's not going to actually be 0 plus. We've got to see what it will become. So we take that function, ln of x, and we say it's t equals ln of x, and we look at its graph. So now we as approach this, we plug x into here. What is our t approaching? So our t, you can see, is approaching negative infinity. So we are approaching negative infinity. And so now you can find the one that works, and it's -pi over 2. And if you get a little nervous on this, you can still check it with your calculator. So we're going to plug the exact limit in there for our function, and we're approaching 0. So what I like to do is plug the other one in there as well. So -2 pi divided by 2. Okay, so that's our value that we want to match. And so now if we're approaching 0 from the right, that looks like this with the calculator. We're going to approach 0, right? Our table start is at 0, and then we're going to go a little bit to the right of it. Well, just a tiny bit. So I have e to the -20 there, so you just go 0.0, 1, 2, 3, 4, 5, 6, and you just sit here and keep entering them. 1. And then we go to our table, and you can see, look at that. It's approaching it. So as we're getting closer and closer, it's getting closer and closer to pi over 2. And so if you want to get even closer, hopefully I didn't zero it out. It's going to give me an error now. But no, you can see now it's even closer. And so as we're approaching infinity, basically, we're approaching 0 from the right, like this, it's going to approach your -pi over 2. All right, here's another type that we're going to run into. So this looks very, very similar to what we've done before. So what we're going to do now is use the x at infinity on this function. So just this all by itself. So what we're going to do is go over here and go the limit as x approaches infinity, just like we did up here. We looked at the limit as x approaches 0 from the right of just the natural log of x. And we're going to look at it here as well. So 1 plus x squared over 1 plus 2x squared. And we're going to do what we've done before, and that's divide everything by x squared. So this would be the limit as x approaches infinity of 1 over x squared plus x squared over x squared. 1 over x squared plus 2x squared over x squared. And that gives us the limit of 1 over x squared plus 1, 1 over x squared plus 2. And then now we can apply our limit to infinity for our fractions. That goes to 0, and that goes to 0. And so we get 1/2. You can write the whole thing if you want to be very precise and say 0 plus 1, 0 plus 2 to show all the limits, and then you have a half. So now we know as x approaches infinity, this is approaching a half. So we end up with inverse cosine of a half, which is pi over 3. And again, we check it the same way. We're going to infinity here. So we set our calculator up with our function, our pi over 3. And then our table set now is something really, really large. So make it something, you're never going to get close to infinity, but you can replicate something similar to it with a calculator. All right, I think it's done. Change in table is 1. Doesn't really matter there because it's infinity. And then we go to our table, and you can see that they match perfectly. So everything is perfect. It's pi over 3. And there you have it.